let's start. Okay, it is me again. So our next speaker is OSKAR, who will show you how the wave function collapses. I told him I'm going to make a joke, so I had to. Please welcome OSKAR.
Thanks. Oh, wow, now it's working. Yeah. Hello, everyone. Yeah, I'm OSKAR Stahlberg. I'll be talking to you about my new project that looks like this, that I am currently working on. The talk will be quite technical, probably more technical than a lot of the talks so far. But I'll start by just introducing myself. My name is OSKAR Stahlberg. I've worked in video games for like 7 years now, I think. I started out at Ubisoft Massive. So my first project I worked on was The Division, where I made this cool holographic map. And sort of maps and urban environments has been a big part of my work ever since. In the middle here, you see two web demos I did a long time ago. Those are accessible online. You can play them in browser and build your own little house or build your own little planet. So I'm very interested in procedural stuff in general, and the talk is going to be a lot about procedural stuff. And the last GIF you see here is from the game Bad North, which is the past 2 years I was working on the game Bad North. So it's a small procedurally generated micro strategy game where you defend islands against Vikings. That also started as a procedural project, like all my projects do. And then I was kind of at a good place in my career where I figured, well, might as well put a game on top of this and do my first indie project. Yeah, but that's all out now. It actually shipped on mobile 2 days ago. So now we've shipped on all the platforms that we were going to ship on. Yeah. And if you want to see cool GIFs like this, you could follow me on Twitter. That's my Twitter handle right there. But today, I'm going to talk about my new project. It doesn't have a name yet. The working title is Placemaker, because you're building nice little places, kind of. But this is what it looks like. And it's kind of a combination of a lot of themes I have been working on lately. So it uses a lot of the same core ideas from Bad North, but it also combines it with the things from Brick Block, that thing where you build a house, and a bunch of other stuff. And then it introduces the new way of doing a non-square grid. You can see, so we can create kind of more organic-looking tiles, which is something I've been wanting to try out for a very long time. Yeah, so I'm gonna talk about just the different techniques that go into making this thing. So first of all, what is it? It's a mix between the algorithms marching cubes, which is quite a simple algorithm that's a good first procedural algorithm to implement, and the algorithm wave function collapse, which is a bit weirdly named algorithm, but it's an algorithm for placing tiles inside a space. So it's a mix between those, and then it's also running on an irregular quadrilateral grid. So quadrilateral means that all the, you see how the little black grid here, it's all made of squares. Or not squares, it's made of quads, right? So they all have 4 corners. But it's irregular, right? Here you have 3 quads meeting at a corner. And you can build there if you want to. Or here you have 5 of them meeting at a corner. And you can probably, yeah, there's 6 of them meeting at, oh, that's too far away. Oh, I can build like that. There we go. So I'm going to start to talk just about how I am approaching the generation of a grid like this. It took me some time to, I knew I'd been wanting to work on a grid similar to that for some time, but it took me a while to figure out the best approach for it. So I'm gonna just show you, some of you might have seen this GIF on Twitter before. So that was the only slide. Now it's just gonna be in Unity and a couple of pictures. So here you can see how the grid is made. So I start by creating a bunch of triangles within a hexagon, and then I randomly join some of the triangles into quads. So that's the only random element in creating the grid, because after that, the grid, if I just seed that with the position of that particular grid patch, then it's deterministic. Yeah, so then it randomly joins some of the triangles into quads, and then it subdivides all the quads and all the triangles, because obviously you can subdivide a quad into 4 new quads, but you can also subdivide a triangle into 3 quads. So it's if you run the smoothing algorithm, smoothing function in any 3D software, that's basically what it does. And then I run a relax algorithm on that to make it all kind of smooth and nice and not jagged and sharp. Yeah. So I do that, and the point of that kind of is the point of using a quadrilateral grid like that well, the point of using it rather than just a square grid is, of course, because like townscapes look more fun when they have fun and interesting organic shapes. I mean, Paris of all towns kind of look like this a lot. But it's also because if it's all made of quads, then you can use square tiles and place them there. So that means it's quite easy to input. Like that's a good functional. You can tessellate squares. You can place them next to each other. They have edges that bump up against each other. So it's like that's how we normally use tiles in games. So it's just a more fun way of using pretty regular game tiles. Actually did some work for. There's a game released like a few months ago called Night Call that takes place in Paris. You're a taxi driver driving around, and they just needed a view of Paris. Like you're driving around on the actual map of Paris, and they just needed a view of Paris that sort of swish by in the rearview mirror as you're driving around. So they contacted me to help them out with that. And that was my first attempt to try out making a quadrilateral grid. So this is what I did for that one. So you can see how like the grid, here it's actually generating it within city blocks that are like the actual blocks from actual data of Paris. But so that was pretty complicated to write because you can see how it gets kind of wonkish around a lot of especially like sharper places. But for my new project, then I wanted to figure out, and there's a lot of, like I have to do a lot of intersection tests because you're kind of tiling it up. You have an irregular polygon, an arbitrary irregular polygon, and then you're tiling it up with quads along the edges, and then you sort of keep filling it in until you fill it in all the way. But if you make a mistake and the quads start sort of overlap each other, then it will all turn inside out, and then it will start building towards infinity. And you obviously don't want that. So that was quite tricky, and you have to do a lot of just line-line intersections and quad-quad intersections and check, like, can I place something here? So in this new project I'm making, I want it to be very performant and be able to run like in the browser or on mobile and stuff like that. So then I wanted a solution that didn't contain, where I didn't have to do any intersection tests and stuff like that. So I'm very happy that I figured out this model. Yeah, and we can actually see, let me show you it generating on the fly. So now the game's running, so we'll turn off the game, and then we will I can tell the game how fast its update loop is supposed to run. So now it's quite slow. It's just going to be able to do 8 steps each frame. Normally I run like 8 milliseconds each frame. So we'll see here you can see how like it's building everything, and the sort of tiles are slowly falling into place. There's still some awkwardness, but that will sort out soon. And all these like red things are marking out like where it's supposed to generate new, because now it's just generated a little grid patch in the middle here. We up the speed here a little bit. Yeah, so now you can see it like, now it's generating these little grid patches. And like a challenge here was also, you can't, like a relaxation algorithm, you can only run a relaxation algorithm on a finite set of points. But I wanted this to be a theoretically infinite grid where you could just keep building forever. I mean, obviously you will run out of memory, but you can like build a bit here and then remove those things, build some here, remove those things, build some here. So you can kind of walk by building in different directions. Like if I place a tile like here, it will start to build grid in this direction too. So what I have to do is I have to generate a bunch of these little patches. So here you can see the clear, like the patches made of triangles that are subdivided, that turn into quads. But I have to generate clusters of those patches that I then can, so in clusters of 3, as you can see here with this thing that kind of bends into place, I relax them together, and then with the final result, I can interpolate between a bunch of different of those relaxed clusters, and then you get like a seamless tiling thing made out of quads. So you can see how, like here's obviously the borders between the different patches, and you can see how it all lines up perfectly in the end. Yeah, so now it's generated like everything it has to generate for my current size of the world. But if I keep building this way, yeah, you see how now like it wants to generate more in this direction and a bit more in this, because there's like and a very interesting thing in generating the quad grid this way and starting with generating triangles is I got an interesting opportunity to use something I've been wanting to use for a long time, which is there is a way of thinking about hexagons. Like, has any of you ever built hexagon-based games? Yeah, a few nods. Yeah, okay, a few people. There is a very interesting way of thinking about hexagons where you can think about them as cubes in a sort of diagonal plane, stacked like this. Because as you can see here, these are cubes, but they're also hexagons. And then you can use integers instead of floats for their position, so you don't get position errors, and you can do, like, a lot of the math becomes much more straightforward than if you're using positions and angles and stuff like that. Then you get a lot of floats, and then if you build a very large grid, you start getting floating points issues and stuff like that. So it's a very nice way to approach hexagons. Yeah. And it also makes sure that the grid kind of has this nice irregular shape, right? So none of the quad, like there isn't an underlying square grid that creates this quad grid, but it's all made of hexagons. Yeah, another fun thing with the hexagons is, oh yeah, and if you want to look further into that, there's an amazing article that I've used a bunch of times, written by, like the address is here, by Amit Patel. He does a bunch of, I mean, I'm sure you've come across some of his work before. He does a lot of really interesting, really well explained sort of articles and blog posts about some fundamental, like pathfinding algorithms, ways to structure your grids, graphs, stuff like that, and like procedural generation stuff in general. So I got a lot of my hexagon math from him. Yeah, and an interesting way to illustrate this as well is that since all the verts here have an origin position on this, like as integers, I can actually use, I'll show you the bounding box I'm using to decide like what the center of this world is and how far out I'm going to generate. So this looks like that, and it looks like a kind of a hexagon. But if we build it a lot in one direction, you can see that it is actually a box, but that's projected down into the flat plane into the hexagon space. So it becomes a bounding box, but in hexagon space, which means that you get less of the obvious bounding box center that you would get if it was just a grid-aligned bounding box, the normal way you would do it. So that's a nice little illustration of what's going on. Yeah, so that's kind of it about the... No, there's a few more things about the grid. So yeah, obviously, when I run the relax algorithm to make the grid look as sort of nice and relaxed and smooth as possible, I found an interesting way of doing that. And that could be a general way if you have like an irregular quad and you want to turn that quad into more of a square, but you don't want to align it to the axis of the world you're working in. This is a very convenient and fast and easy way to do that. So you start by like calculating the center, and you get the vectors like from each corner to the center, right? And then if you just rotate them all, like rotate one of them nothing, and one 90 degrees, one 180 degrees, and one 270 degrees. And the way you can rotate a 2D vector is if you just flip the coordinates and invert one of them. That's a 90-degree rotation of a 2D vector. So that's a super cheap way of doing it. So you rotate them, and then you average them, and then you rotate them back out, and then you just move towards that, right? So then you get a perfect square. In the end, of course, in my relaxation, I can't make a perfect square out of them because, like, I could make a perfect square out of one grid, but since they're all butting up, or one quad, but since they're all butting up against each other, I'm sort of accumulating these little forces, like you see the little red, green, blue, yellow force on these corners. I'm accumulating them from all the, like for each vert, for all the adjacent quads, and then I sum them up, and then I do that over multiple iterations. And that's actually one of the slowest parts of the, one of the slowest algorithms that I have running, the relaxation, because you have to do it quite a lot of times. Like when you saw the grid relax in the beginning, you could see how like it actually takes a while to relax all of them, and it keeps like it's still having effect even 256 steps out, which is how fast I'm running it. Yeah. So that's the grid I'm working on. Another interesting thing I do with the grid is I want to create like sort of different areas that are like some of them are more chaotic and some feel more orderly. So you can see how some of these hexes are like this. Here you can clearly see the remnant of a triangle, right? And here's clearly the remnant of a triangle. Whereas this piece here is just made out of 6 very big triangles. So this piece becomes much less chaotic than this one here that's made out of more, anyway. And this one here is made of a ton of small little triangles. Like you can see how the triangles is kind of made up of, like here's the mid-level, here's the very, very big triangles, and yeah, this is the more chaotic one. So these end up like, if you build around those areas, you get a much more chaotic looking town with like weird wonkish shaped houses. Like you see, like that's a weird house shape, obviously. Whereas if you build in the more axis aligned areas, you can build nice, big, squarish functions. So that's kind of an option I want to give the user in the end to kind of choose what kind of style they want to build their environment in. But I don't want them to be able to build a completely square thing too big. Like they're always supposed to butt up against the sort of organic nature of a city. And that's kind of one of the fundamental sort of aesthetical things of this project is I really like in urban environments, I really like the combination of the artificial and the planned and the symmetrical, which is like whenever you build a house, usually, well, not anymore, but it used to be, that you build it kind of symmetrical with a clear sort of idea and repetition and patterns. But then, you know, it always butts up against another house with sort of a weird angles, and you have to make it a bit of a weird angle. And then after a while, when you renovate it, you change like half of the house slightly or so. In the end, you have this sort of organic asymmetry growing. So new symmetrical things keep popping up, but then they kind of become more organic and symmetrical as the environment grows around them. And that's kind of a thing that I want to, an aesthetic that I want to work with in this game. I'm hoping to add later, like right now I just have these little grassy patches, but I'm hoping to add later stuff like plants that actually grow slowly over time. Like vines growing on the walls would obviously be ideal, but even just little trees or whatever, stuff like that, that kind of grows slowly over time. So obviously this is a very tile-based thing. So if we just look at how it all comes together, let's turn off the grid, this grid too. So these are, here you can see how it's all divided into little tiles. And these, for this project, I have to build a lot of tiles to make the whole thing work. So this is actually what it looks like in Maya when I'm building them. So that's quite a few tiles. I'm up to about 200 tiles already, but I reckon I'll have to build like 300 or 400 to satisfy all the possibilities of whatever you can build. And so these tiles look very similar to something that you would use for a normal marching squares algorithm. And one core idea is that the tiles sit on kind of the corners, right? So if we select a small little house piece here, so this is just a single block of house, right? But it's made up out of like 4 corners on top and then 4 corners on the bottom like this. So each of these little modules have, like this one obviously only has 1 corner that's sort of inside the house block, whereas it has like the rest of the corners are outside the house block. So we can look at what that looks like. So here is all these tiles imported into Maya, but they don't have a texture here. This mesh here is actually just for debug purposes for me to be able to see what I'm working on. And here, incidentally, is actually the different tiles I'm building being recombined into bigger tiles, because I don't want to have to build all of these weird combinations myself. So whenever you have tiles that could fit, like you could have a corner like this against a corner like that, and they're not intersecting, I might as well just generate that out of the meshes I already have instead of building it manually. Because there's a lot of combinations to build. Obviously, this like goes into forever here. And here also you can see how, let's pick the thing we were looking at before. Here's that little thing. If we select this one here, I should be able to click on it. And yeah, oh, it's a bit slow when I try and display all of this. So here you can see how it has a little square on the, or a little cube on the corner here. That's because that's the only cube that's inside. Whereas if I click this piece of wall here, it has 4 cubes because it has 4 corners that are inside and it has 4 cubes that are outside. So that means, of course, that you can, like taking those corners in sequence, you can combine them into, right? If it was just inside and outside, it's not that simple. But if it was just insides and outsides, you could put it into just a binary number, right? So this one here could be 1, 0, 0, 0, 0, 0, 0, 0. So that's like that's 1. Or if the corner was placed here instead of here, then it would be 0, 1, 0, 0, 0, 0, 0, which is 2. So that's a great way. You can just index them like that, and then when you ask for them again in the algorithm, it's very easy to just access the right one straight away. Now, in my case, there is one pretty significant piece of complexity above that, which is that I want to be able to use multiple colors. So if I build, run the game again, if I build with more than one, if I build with like colors of blocks of different colors next to each other, I want to like make a little comment in the mesh of what happens when those 2 blocks meet, right? So here you can see, oh, let's make it run faster. There we go. So here you can see how this green meets the yellow. So then there's like a little trimming like this, and it has like a slightly taller window. And when these ones meet each other like that, there's a little bit of a drain pipe. Yeah, basically I want to be able to, and here these meet and they have like slightly different heights. So I want to be able to comment what happens when different colors meet. But that also means that I have to, like, it's not enough to have a like a house corner like this. I need to have a corner where like the top, or a house side like that. I need to have one where the top part is one material color and the bottom one is another material. This doesn't only work for green and white though. Like whichever color you choose, you can pick this one and then recolor them, of course. So I have to do that one, but then I also have to do like, okay, what happens if we split the colors this way around, and what happens if we split the colors, like here's one that splits them in 4 different ways. So then I have to like assign different colors and build all these kinds of different combinations. So that's a lot of work, and that's why I think I'll need another. If I didn't have the different colors, I think I only would theoretically need 67 pieces to make this whole thing work, but with the different colors, the permutation count kind of explodes. So now I think it will be like in the 300-400s or something like that. Yeah, so the marching squares part, the marching cubes part of the algorithm, that's the simple part. That's the part that can figure out that, that this is a corner and can place the corner on the corner of a house. But that's not all it takes, because obviously I have a bunch of different types of corners, right? So I have this top corner here, which is like a simple type. I have, now it became a different type, but then of course I have like this little corner here, where it's like a terrace, or this little thing here, where it's like a bigger roof, and there's all kinds of things like that. So that's where the wave function collapse algorithm comes into place. So let's see if we can actually see this unfold in real time. So if I turn on the gizmos, I select the, that's the graph I need to select, and then turn on off the graph. There we go. So, no, that's the wrong one. Yeah, OK, I think this should work. Yes, so here it became very, very slow, and now it's the drawing of everything that's very slow. So what you see here, the white wireframes you see, is the entire possibility space, right? So for each of these little slots, there are a bunch of different modules that are possible, but it's usually not that many. Like on a corner slot, maybe there's like, I don't know, 20 different ones, because it's like a few different styles, but then they can be rotated and mirrored different ways. So it starts with all of those being, so let's just maybe look at, it's a bit slow if you have everything selected. So let's maybe look at them here. I think it's still, yeah. So here, if you look at this corner, you can see kind of the shadows of, let's turn on the wireframe, the shadows of the different possibilities. You see, like, it could have a chimney here. It still thinks it could have like a pointy side and a chimney here. It actually can't in the end, because there would have to be a similar chimney on this side, and there's not. But it doesn't know that yet, because the algorithm hasn't gotten that far yet, right? So right now, this thinks that there are 11 possibilities for this cube, and those are the ones we see here. And this one thinks that there are 10 possibilities for this one. This only thinks there are 8. Like you can see the shadow of the kind of trimming we were looking at before here. But as the wave function collapse algorithm runs, fewer and fewer things are possible, and in the end, it all collapses. So if you just run it again, if we select everything, we see all the gizmos for it. Yeah. And so obviously, the wave function collapse is an algorithm that can be quite slow. I've managed to build my thing in a way so that I can run it, like if we run it very slow, and I can keep clicking, and even though it hasn't finished figuring out what things are supposed to look like, I can still keep building. And then it will just like, if we just make it faster again, OK, now I selected it, so now it's very slow. Then it will kind of resolve it all anyway, after the fact. So there's like 2 kinds of propagation happening. First, there's a propagation where, like, if you build something, it needs to propagate out and tell all its neighbors, like, hey, something changed, so everything's possible again. And that one tells its neighbor, hey, I changed, and that means I could have a different side towards you, so that means everything's possible for you again, and that kind of propagates out. Obviously, if you have disconnected houses like this, it won't propagate to them. So if I select all of these and build here, it might even be so fast that, yeah, because if I build here, you see how this entire chunk becomes, like, everything becomes possible again, and then the possibility space collapses, and yeah. Whereas if I build over here, these aren't connected to this, but if I connect them like this, then yeah, that all happens. So I have done a longer talk, like hour-long talk on just the topic of wave function collapse for anyone who wants to dive deeper into that. So that's the name, again, of the algorithm that kind of figures out which pieces fit next to each other and selects them. But the core idea is, like, you build a large possibility space where everything's possible. In my case here, not everything is possible, because just the right, like, corner pieces or side pieces that satisfy the constraints around there are possible. And then you start removing, as soon as you places one piece, that means that a bunch of the pieces next to them are not possible anymore, so then you start removing those, and then that means that a bunch of other ones are not possible anymore, and that propagates, and the whole thing collapses, and in the end, there's just one possibility, and that's what you end up showing the player. That went by way quicker than I thought, because I have a bunch of other things, but maybe we'll cut for questions or wrap it up, maybe. Yeah, OK. But I'll have this project running on my computer, and I'll be sitting around somewhere. So if anyone has further questions or want to take a look at anything or stuff like that, then you are most welcome to approach me. Thank you.